For this video, let's talk about the common limit theorems for complex numbers. Now, these limit theorems are actually just similar or patterned to the limit theorems for functions that involve real numbers. But this time, so we're talking about complex numbers, so we will be using functions of z. Now, let's say that if the limit of, let's say, a function of z where z approaches z sub 0 is equal to a certain value of a, and the limit of another function, which is a complex function, you have as z approaches to the same, okay, z sub 0 is equal to b, then the following theorems hold. The first one, okay, is this limit for the sum. Okay, that would mean if we have here the limit of the sum, let's say we have a function here which is equivalent to the sum of the two given functions f of z and g of z as z approaches to the same value z sub 0. This is equivalent to simply the sum of their equivalent limits. Okay, this is the first limit theorem. But of course, this is a theorem. We just need to show that it is true. This may not be enough for this video, but allow me to do the same or a certain representation. Of course, a theorem will allow us to distribute this limit here. So you have here the limit of your function of z as z approaches to z sub 0. And you have here plus the limit of your g of z as z approaches to the same z sub 0. Okay, as you distribute that, that is why the limit of this is actually equal to a, and the limit of the second is actually equal to b. This shows that this limit theorem for the sum of functions is true. Again, given that we already have the limits for the two functions as z approaches the same z sub 0, and if we have here a combination of them, simply add their corresponding limits. Now, the second item here is just the similar to that, but we are talking about the difference. Okay, let's say you have here f of z minus g of z as z approaches to z sub 0, the same value as this. Okay, this is equivalent to the difference of the equivalent limits a and b respectively here. Take note, it's subtraction, so there is no commutativity for that. We need to really write it properly. Of course, again, the proof of that is by distributing, okay, the limit notation. So you have here the limit of your f of z as z approaches z sub 0 minus the limit of your g of z as z approaches to z sub 0. This is actually a and this is actually b, hence this is again true or will hold. So if you have some examples later on, you'll actually apply this limit, these first two limit theorems. But of course, we also have the idea of substitution of whatever the value of that here. Simply substitute that. But definitely, we will be using the same process if we're going to look at it in a bigger and more comprehensive picture. Now, let's proceed to the next two. Okay, let us have here the third limit theorem, and this is for the product. So you have here the limit of the product of your f of z and g of z complex functions as z approaches to z sub 0. If we have here the limit the limit of the product of two complex functions, we are just going to have the product of their corresponding limits as well. Now, for the proof of this, we know that for this to be a product, we have a similar perspective on our limit theorem for real numbers, where we can simply make this as a product of their corresponding limits as z approaches the same z sub 0. So we have here that, and we have here in the second one as z approaches z sub 0. Okay, so this is not necessarily distribution because these are under multiplication, but we share it to both, and we know this to be equivalent to a and this is equivalent to b, hence again this is true on that, or that will hold. Okay, now let's have the fourth one. And the fourth one is, of course, to complete the fundamental operations, the division. So if we have here the ratio of f of z and g of z as z approaches to z sub 0, okay? So given that, okay, where your g sub z is not equal to 0, okay? That would mean this is equivalent to the ratio of A and B, also given B is not equal to 0. Okay, so basically similar to what we did in multiplication. So the limit of this one here could be distributed to the numerator as z approaches to z sub 0. Sorry for that. That's z sub 0 all over the limit of your g of z as z approaches z sub 0. And again, this is equivalent to your A and this is equivalent to your B. Hence, this would hold again for this restriction. These are the limit theorems for the fundamental operations. We have addition, subtraction, multiplication, and division of complex functions, which are also applicable for complex numbers and real numbers. Now, talking about the rest of the possible limit theorems, just like for the roots and etc., that will use this first four fundamental limit theorems, then that will also hold. We will have some examples of this to illustrate the value of a certain limit, provided that we have an exact value for z sub 0 for the given function. Thank you very much for watching.